This is precalc. This is 2.4. This is the first day. We will take 2 days on this. Is talk about average rate of change and the increasing and decreasing functions. All of this stuff has been taught to you in Algebra 1, for sure, because I just taught it about a week or so ago. But we're just going to use it in a little different fashion. We're going to talk about it in a little bit different fashion. The first thing I'd like to talk about before I get into any kind of formulas and what things are is that let's talk about a little situation here. We're going to take a drive of 120 miles, and it's going to take us 2 hours. You guys would say your average speed or rate is 120 miles for 2 hours. That's 120 divided by 2, 60 miles an hour. So you would say, hey, I went 60 miles an hour for this trip, on average. But I think we all can agree that if we got in our car right now, we're not instantaneously going 60 as soon as we shut the door, right? And we don't just all of a sudden stop on a dime and say, we're done, we're here. There's other things that go on in between. For here, if I was going down the highway, then maybe I could say, yep, I was going 60 miles per hour, I just locked it on cruise and I just went. But if we're traveling to the highway, we got to maybe stop at a couple stoplights. We may have to speed up on the on-ramps, slow down on the off-ramp, all those things, right? All considerations. But we still, if we went 120 miles within 2 hours, we still would have an average of 60 miles per hour. Would you guys agree? Mm-hmm. But I think also, given that situation, that if I started taking intervals of something smaller than just 2 hours, then you would start to see some things that are happening, like the graph we have. If I start to say, let's take it every few minutes or every few seconds or whatever, or continuously, right? Because that's why the graph is connected here. If we continuously contract our time to distance, you can see that it increases a little bit and then kind of steadies out for a while, and then it increases again, and then starting to plateau. So something's happening. If I took the time interval, instead of saying the whole entire thing from here to here, which would be 60 miles per hour, that's my average speed, what if I cut that and only did those two? An interval from the time I started to about halfway. You think that's still 60? No. It might not be, right? Could it be? It could be. It could shake out that way. But really what we're doing when we take the average rate of change, guys, is we are starting at some point, stopping at some point, and all you're doing is finding the slope. What's the change going on between those 2 points? What if I change the colors? I still start at the first half, but I end here. Which one's going to have a bigger rate of change? The black line or the red line? The black line is going to have a bigger rate of change. Or if I go and make it a blue line now, or purple, connecting the halfway to the end. Now all of a sudden it looks like you definitely had a larger rate of change in the second half of your trip than you did the first half, right? Maybe you all of a sudden get halfway there, you're like, I'm going to be late. So what do? You speed up. Which will definitely affect your overall average rate. So obviously, will the average speed be the same over different intervals? And the question, or the answer would be, no. Average. Average is all about adding things up and, even things out, right? So you could be going different rates at different times. And on the bottom there, big paragraph just kind of talks about that these are very important in the real world. You may be interested in knowing how quickly the temperature changes, big storm coming. Maybe there's a correlation between the faster your temperature drop, the stronger your storm is. Or maybe it's coming to you faster. Increasing or decreasing revenues from a new product. It'd be good to kind of know how fast is that changing. Should we increase the price, decrease the price? Should I make more of these things? Those are all things that people in real life actually use the rate of change for. So what is the rate of change? We already kind of hinted at it was slow because, yeah, it's there. the average rate of change, guys, for this function, doesn't matter what we call it, we're calling it y equals f of x, is between, now they use x equals a and x equals b. So kind of like a start and a stop point. Most of us would rather see x1 and x2. Because average rate of change is the change in y's over the change in x's. But we said y up here was f of x. So instead of using y2 and y1, they use function notation. They plug the values of x that we're putting in this case a and b, in. So therefore we have f of b, that's like f of x2, minus f of a, which is like x1, over x2 minus x1. So that is the slope formula, y2 minus y1 over x2 minus x1. And the cool thing about it is all of those, that black line, red line, and blue line from the last slide, those were what we called secant lines. And it says the average rate of change is the slope of that secant line. And so, like we have here, if I connected these 2 points, and I'll do that here in purple, the slope of that purple line, that secant line, is the average rate of change. And obviously, the bigger the interval, it can change your average rate. So your interval will dictate what your average rate will be. Okay, any questions on that? A lot of times what we like to do is we always like to keep our A being our ones closest to 0, B would be the value that's away from 0. We generally like to do that because we like to have positive slopes, but do I need to necessarily go from A to B? No, because we know slope goes in both directions, it's going to still be the same. So it does not matter. So for today, all I'm going to do is give you 2 to 3 different equations and then ask you to find the average rate of change, or the average rate of change, reach from certain points to other points. The first 2 is from 2 to 6, and then the next one's from 5 to 10, of f of x equals x squared plus 4. And we're going to kind of take a look and see, does that make sense or not? Because there's a lot of things about graphs that you know. And then the last one takes the numbers away and brings back the a and the a plus h. And you guys are going to see that's really familiar. That's something you've already seen. So I want to find the average rate of change, so I probably should write down the formula. I'm using it. Write it down. Average rate of change. I'll just call that abbreviated ARC just to save a little space. Average rate of change is f of what? F of, generally they actually gave it to us as f of b minus f of a. It would not matter the order there, but whatever you put for your order here, what goes underneath? B minus a. So if you have f of a minus f of b, then you better put a minus b. That'll help wash out any signs that end up popping up, right? Also, because we're talking about functions and them not being so nice, sometimes, like we got things that are squared in this one, other ones might have fractions, I would use parentheses and brackets, because you're eventually going to have to subtract f of a. So, b and a. So a, let's call a the 2, b is the 6. Yes? According to the logic that they were using, because 2 comes before 6. So, that means that it's 6 squared plus 4 minus 2 squared plus 4. All over. What? 6 minus 2. What's 6 squared plus 4? 40 minus 2 squared plus 4. 8 all over 4. 32 over 4. Which equals 8. Bless you. Any questions on that? Pretty straightforward. Do it again. 5 and 10. A and B. 10 squared plus 4 minus 5 squared plus 4 all over 10 minus 5. 10 squared plus 4. 104. Minus 29 all over 5. 104 minus 29. 75 over 5 equals 15. Okay, I'm going to stop here. What does this mean? 8, 15. They're just numbers to us right now. What were we finding again? Slope of the secant line, or the average rate of change from over a certain interval. Does it make sense that for this particular problem that those would change? And change by that much? What kind of graph is that? It's a parabola. Okay. You guys know some things about this parabola. You do. What do we know about this parabola? What's that? We'll get to part C in a second. Jacob, what are you saying? It shifted up 4, and we know that it opens upward. So would you guys agree that it would be something like this? Okay? I got no scale on there. I'm just saying it's moved up 4. Okay, let's take a look at our intervals, guys. The first interval is from like here to here, right? Which would be that slope. What's the next one? The next one would be slightly back further, but then over further, right? As the parabola gets further and further away from the middle, any secant line there would have a what? Steeper slope. Right? And so if I start getting over here, all of a sudden now it's going to start getting more vertical and more vertical and more vertical. Notice that if they would have gave me an interval on the other side over here, I actually would have had a negative slope, right? I also could, if they would have gave me a point straight across, I could have had a slope of 0. Average rate of change, it'd be like, oh, there was no change going on. Because I stopped and started at the same height, right? Very interesting. You kind of have to know things about your graphs. Or you know some things about them that can help you understand why one is 8 and the other one's 15. Last one. I'm assuming that A can be A, and then the A plus H must be the B. Is everybody okay with that? This will be an interesting one. So A plus H squared plus 4 minus A squared plus 4 all over what? A plus H minus A. I think everybody can get the bottom. That's going to be no big deal, right? The bottom just becomes H. The top, though, needs to be cleaned up. I need to FOIL A plus H. And do not tell me it's just A squared plus H squared. It's A squared plus 2AH plus H squared plus 4. The floors, they're going along for the ride. Minus a squared minus 4. Don't forget to distribute the negative in, and on the bottom it just becomes h. Is everybody able to follow that? Ooh, I like something that happens here a couple times. What happens? A squared's 4's gone. So now I'm left with 2ah plus h squared all over h. And I even like this because what happens? I'm going to factor an h out first before I cancel. So I get 2a plus h all over h cancels. So the average rate of change is from a to a plus h is 2a plus h. Hey, wait. I guess without having numbers in there, it doesn't kind of mean much to me. But I suppose if once I know a or an h, I could. But wait, let's go back up to this thing. Wait a minute. Where did we see this thing before? Didn't we just do that on the first lesson of this chapter with evaluating functions? And they actually had us put in a plus h, f of a plus h minus f of a all over h. And that's what technically just happened here. Man, they just keep on throwing that whole long derivative thing back at you. Guess what a derivative finds? Slope. So therefore, that's why you get this, because that's the slope at a given point, at any given point, not over 2 points. It's what happens, guys. This is the thing about slope. You see these, we took these points over here. What if I started making them closer and closer and closer to each other, and to the point where they became the same exact point? That's instantaneous slope. That's called a derivative. It's pretty cool stuff. You guys will do that next year, hopefully. Should be good stuff. Any questions on this? Feeling pretty good about it? So then do that one. This one is, if an object is dropped from a height of 3,000 feet, its distance above the ground in feet after t seconds is given by the equation h of t. T is a function of h, or h is a function of t, sorry. Height is a function of time, equals 3,000 minus 16t squared. Remember, this is not being thrown into the air. This is just being dropped. Find the object's average speed for the following times. Between 1 and 2 seconds, and then between 4 and 5 seconds. I'll pause it. I'll let you guys try those. So again, average rate of change. So we got f of b minus f of a all over b minus a. I'm going to write down the formula again because I'm going to use it again on a new page. So 3,000 minus 16 times 2 squared minus 3,000 minus 16 times 1 squared all over 2 minus 1. Everybody hopefully has that so far. The first one is 3,000 minus 64 minus 3,000 minus 16 all over 1. So I really don't care about the 1 anymore. That'll be gone. What's 3,000 minus 64?
2936.
2936 minus 2984. Wait a minute. That gives me a what? A negative 48. What does that mean, guys? It's a negative slope. But what is slope again? Slope is a rate of change. Rates are speeds. Yeah, it's per second. It's what per second? Feet per second. That means at that interval, you're changing 48 feet per second. Yep, there's a negative change of 48 feet for every second. We're dropping the object. Wait a minute, we know this graph is a what? What kind of graph is that? It's a parabola. So it's going to be something like this. Actually, if you're talking about dropping it, I'm assuming you're just on the positive half, right? So, what happens as an object is falling? It gets faster. So the further I go away in this direction, you would think between seconds 4 and 5, the slope actually should be bigger, right? Or more negative. Okay, let's test that out. So it'll be 3,000 minus 16, sorry. 16 times 5 squared minus 3,000 minus 16 times 4 squared all over 5 minus 4, which is again 1. 3,000 minus 5 squared, 25 times 16. 400 minus 4 squared, 16. 16 times 16. 256 all over 1. Actually, last hour I did this backwards. I did from 5 seconds to 4 seconds. Still came up with the same answer. 2,600 minus 744 all over 1. Subtracting those two is a negative 144 feet per second. You're cruising, right? That object is falling pretty darn fast. And obviously, guys, if I went from 0 seconds all the way to 5 seconds, it'd probably be somewhere between those two, right? Because it would be a little bit less steeper going from here to there versus, 4 to 5 seconds. Okay? Homework for day 1, page 182, 3 through 5, 11, 15, and 16. Have a great day.